This chapter is about the fact that when a conductor is connected to a source of EMF and when current flows through this conductor, it produces around it a kind of effect which is exactly identical to the effect produced by a bar magnet. That means this electrical energy passed through this conductor is transforming the arrangement of the atomic setup of the conductor in such a manner that they get polarized, which changes the behavior of the whole conductor, and it produces a kind of field around it which is exactly same as a bar magnet produces usually. So basically আমরা যদি একটা কন্ডাক্টর এরকম করে চিন্তা করি, কন্ডাক্টরের ভেতরে অ্যাটমসরা আছে, and since this is a conductor, so by natural way it contains large number of free electrons, and those electrons come out from which atoms? They all turn into cations. So all those cation electron pair stay steadily inside this conductor when this is not connected to any source of EMF. But when it is connected, then a driving force, suppose this is cation and this is electron, this is cation, this is electron, this is cation, this is electron. So they arrange randomly all over the lamina, but when it is connected to a source of EMF, a driving force, that is electrical energy, enters into the material and tries to orient these pairs in such a manner that polarity starts gaining inside this material, and for which it produces its own magnetic field around the conductor. And this is usually called magnetic effect of electric current. Now if we place a magnetic needle below it or above it or at any point around it, and when the current starts flowing, its north pole is seen deflecting in this way or that way, and if we reverse the direction of the current, then the deflection's direction will also get reversed. That means when current flows through this, it will produce its own magnetic field, and in that magnetic field this magnetic needle is placed. It is comparatively weaker field which is deviated by this stronger field. Now Fleming's right hand, or sometimes called palm rule, and this rule states the direction of the magnetic field produced by any current carrying conductor, According to him, if we place a current carrying conductor on any plane and the current flows in this way, and if we grab this conductor with our right palm in such a manner that the thumb directs the current, if the thumb shows the direction of the current, then the other four fingers kept together will show the direction of the magnetic field. Now if the thumb shows upwards direction of current, then the magnetic field produced is vertically inwards, away from the observer. I am the observer, আমার থেকে দূরে সরে যাচ্ছে, inwards on the plane, and this downwards magnetic field is usually denoted by a cross sign. But if we change the position of this point towards this end, then the current's direction is same, but the magnetic field's direction is vertically upwards or outwards, and that is denoted by a dot sign. Second point is, if we do not change the position of the point, but if we change the direction of the current this way, then the direction of the magnetic field will also change. And if we change the direction of the position of the point and also change the direction of the current, then also it will change. So that means the direction of the magnetic field depends on two things. One is the position where we have to determine the direction of the magnetic field, and also on the direction of current. On these two factors, the direction of the magnetic field produced by a current carrying conductor depends. Usually, now we have to determine the magnitude of the magnetic field produced by a current carrying conductor. And to do that, there is a law called Biot-Savart law. Two scientists, after their name, this law is framed. Suppose here is a conductor and we assume that it carries a current of I, and let's consider a very small part of AB of length dl on it, and a point is selected at a distance r from this element at P, where the magnetic field is to be determined. Now this line is called radius vector. Radius vector. Why is this called so? Because if we consider a conductor and this point is changed around it, like this one, if the point is here or here or here or here, every time the direction of the magnetic field, obviously A je plane আছে তার সঙ্গে perpendicular plane তে magnetic field stay করবে, and that plane is like this. And when we consider this location, the magnetic field's direction is like this one, along the tangent. If this is the conductor, here is the point, then the magnetic field is like this. Usually magnetic field is denoted by B. If the point is located now here, the direction is here. That means at every new point, the direction of the magnetic field changes. All these are R. So R not only denotes the distance of the point from this element, but also it is responsible to indicate the direction of the magnetic field, which changes continuously along with the change of the position of the point. So it is a vector, and it acts like a radius of this circle on whose circumference the points are located, like this one. Suppose this radius vector makes an angle of alpha with this element. According to Biot-Savart, the magnetic field produced here, এটা B না লিখে dB লেখা হয়েছে because this element is very small, dl. We do not consider the whole conductor, but a small element. So the magnetic field produced by this small element is very small also. So it is dB. So according to them, dB is directly proportional to the value of the current, sine of the angle made by the radius vector with the element, length of the element, and inversely proportional to the square of the distance. So combining all this, dB varies as I dl sine alpha by r square. So obviously equal sign comes with a constant of proportionality. This constant's value is mu upon 4 pi, and this mu is called permeability of the medium. What is permeability? It is very much identical to the permittivity, which we have read in the chapter of electrostatics. It is the capability of the intervening medium. Suppose here is the point and here is the current carrying conductor. So this is all the region where the magnetic field is produced around this conductor. And here, there is a medium. So this medium strength to allow the magnetic field to reach here. Magnetic field basically is represented by certain invisible parts called flux lines. Flux. If the number of flux lines passed through unit cross section anywhere, if that number passed through unit cross section perpendicularly at any position is very high, that means the magnetic field produced is very strong and the intervening medium is very good conducting also. So this is the capacity of any medium to allow the number of flux to pass through it. For air or vacuum, mu transforms into mu naught and it is called absolute permeability. And then dB is equal to mu naught upon 4 pi I dl sine alpha by r square. The value of this whole part constant is equal to 10 to the power minus 7 Tesla meter ampere inverse. Tesla is the unit of magnetic field and the symbol of magnetic field is B. This is Biot-Savart law. Now by applying this law we can determine the magnetic field produced by a conductor of different shapes at any position. So application of Biot-Savart law. First, magnetic field due to a straight conductor. If there is infinitely long conductor, suppose it carries a current I and we consider a small element like previous discussion of length dl, and from it, suppose from this conductor at a distance of x, a point P is considered where the magnetic field is to be derived. Now joining these points with the elements terminal points, and then we draw a perpendicular on AP. So this is R definitely, and this is alpha. This is perpendicular. So by Biot-Savart, if this is the magnetic field produced here, by Biot-Savart dB is equal to, if we consider that the medium is air, mu naught upon 4 pi I dl sin alpha by r square. Suppose this angle is d theta and this angle is theta, and this perpendicular's name is BD. Now if in this case we have to replace this sin alpha, how? In this triangle, what is the relation between AB and BD? AB by BD. BD by AB, BD by AB. That is sine of BD forget about that. Now this is theta, this is 90 degree. So this angle, obviously 90 minus theta, so alpha is equal to 90 minus theta. Now since these 2 points are extremely close, so these 2 points are also extremely close. Suppose if we consider this is the part of a total circle, so this will be the center of that circle and this is obviously radius. So we can easily ignore this part. That means we can assume that these two straight lines BP and AP are almost same. Almost same since AB are close enough. That means if this is 90 degree, so this is also 90 degree. This is also 90 degree. So if this is the whole angle is 180 degree, this whole angle is 180 degree. Out of that, this is 90 and this is alpha. So this angle is obviously 90 minus alpha. Since this is 90 minus alpha, and in this case, in this triangle, we have already seen that 90 minus alpha is equal to theta. So this angle is also theta. This angle is also theta. So this angle is theta, this is 90 degree. So this will act as hypotenuse. This is base and this is perpendicular. So BD by AB definitely is cos theta. BD by AB is equal to cos theta. That means BD is equal to AB cos theta. That is DL cos theta. Now, previously in circular motion, we have learned that in a triangle, in a circle, what is the relation between this angle, this part of the circumference or arc, suppose ds, and this radius? We know that r is equal to ds into theta. ds is equal to r into theta. Linear displacement is equal to angular displacement into radius. So in this case, this is the linear displacement, this is the radius, and this is the angular displacement. So BD is also equal to r d theta. So BD is equal to r d theta. So r d theta is equal to dl cos theta is equal to 90 minus alpha. Theta is equal to 90 minus alpha. 90 minus alpha. That is dl sin alpha. So r d theta is equal to dl sin alpha. This value we can replace here. So that means dv is equal to mu naught upon 4 pi I r d theta by r square. That means mu naught upon 4 pi I d theta by r. This is the final extract of dv. Now in this triangle, this is r and this is x. So in triangle B, সেখানে আমরা একটা নেম দিলাম দিলাম BEP x by r is equal to cos theta. So r is equal to x by cos theta. This value is to be replaced here. So that means dv is equal to mu naught upon 4 pi I cos theta d theta by x. So that means if we consider the whole conductor, actually we have assumed that the conductor is infinitely long. So if we join these two ends, suppose this end up, this end and that end. Previously we just considered a small element of it. Now we consider the total conductor considered up to now. So then this angle will change. This angle, suppose this is theta 2 and this is theta minus theta 1. Or this is theta 2 and this is minus theta 1. Because trigonometrical angle, if we move clockwise, then it will be negative and it will be positive. So that means for the whole conductor, if we have to consider the total magnetic field, then we have to integrate it. So B is equal to integration of this expression mu naught upon 4 pi I cos theta d theta by x from minus theta 1 to theta 2. This will give us cos theta, integration of cos theta, sin theta, theta 2 minus theta 1. That means mu naught upon 4 pi I by x sin theta 1 plus sin theta 2. Now if we consider the infinitely long conductor, if we increase the length, this straight line will move upward and this line will move downward. That means when it reaches infinity, this angle theta 1 and this angle theta 2 will finally reach to 90 degree and 90 degree. So what we can write? We can write for infinitely long conductor, B is equal to mu naught upon 4 pi I by x sin 90 plus sin 90, 1 plus 1, that means 2. So mu naught upon 4 pi 2 I by x.